Yeah. So we're still figuring that out. I'll let you know. Um, basically, I need to let you guys know anyway for physics and this class. So, okay. Um, so let's see, share.
Yeah, I think I heard in San Diego or something like this, college started to like say, oh, we're gonna give everybody A's because oh we feel them and the pandemic is really hard and everything.
What was that, Muhammad? I couldn't hear anything.
Just look up the news.
I'm just, I'm getting really weird sounds coming from your mic. So,
Yeah, it might be my mic. Yeah.
yeah, okay. I want to get that checked out. All right. Come on. It's one last chance to inflict pain and suffering. I'm going to pass on that. All right. Okay, so today we're talking about, so let's kind of recap. In the last class, we discussed Newton's laws. Finn? Okay, thank you.
For your example, I didn't know how to spell echo.
Oh, that's a great picture of echo. Yep. Great.
Which is actually correct.
Okay.
You did, for a while, you didn't know how to draw sound waves.
Okay, I need to teach,
right?
buddy.
Right, Dad?
Right, buddy. Okay. He's learning about bats. So, anyway, so last time we were talking about Newton's laws. So F equals ma, and then we threw in the moment to find Newton's laws for rotational motion, and we worked that out. And we kind of had different cases depending about which point we wanted to sum the moments. So if we wanted to sum the moments around the center of mass, the equation's pretty simple. And then if you do some other point, it's kind of complicated. And last time, and in 17.3, we focused on pure translations. So we said that alpha was 0 and solved the scenarios. Today, we're going to have pure rotational motion. So it's going to be, so we will have handled translations, then rotations, and you can guess what's going to come on Thursday. It's going to be everything, rotations and translations, which, basically more or less random motion of things in a plane. All right, so that's kind of the plan. All right. All right, so if you watch the video, I went through this. I wanted to highlight somewhere here. Uh-oh. Oh, I did it in the whiteboard space. Okay, well, I'll just use theirs. So if you're looking here are the key equations for today. So when you have a rotation you usually want to work in the tangent and normal frame. And so remember, the F equals ma portion, the force equations are for the motions of the center of mass. And they follow F equals ma, and then usually you write it in components and use the fact that the center mass, if it's a pure rotation, then the center mass is going to follow a circular arc. So you can write the normal component's going to have a centripetal form, and the tangent component's going to have an R alpha form. And then, and in fact, this equation here is true even if it wasn't a pure rotation. If you sum the moments about the center of mass, it equals the moment of inertia about the center of mass times alpha. So this bottom equation would always be true. It may not be the most useful though. Next one. And in the video, I describe how you can rewrite things in terms of summing the moments about a different point. And the place that you usually do this is where, like, if you have a pinned spot or a hinge or, I don't know, a motor or something for generating a torque. Anyway, you would, the first two equations are the same because that's how it is. F equals ma for the center of mass. But then the moment equation, if there's no translation, looks like this. It looks very similar. So the moment you sum the moments, not about the center of mass, but you sum the moments about some other random point called O. And so the simplicity of this third equation is only due to the lack of translation. So, but it looks very similar to what would have about the center of mass. This one is true always. This one is true when there's no translations. If there's a translation, there's another term that pops up here. Hopefully these look familiar because these are exactly the kind of rotation problems we did in Physics 1. So it really works just like in Physics 1. And these problems we're going to do today, I think, are super easy because they're just what we would have done in Physics 1. To be honest, the examples we have here are probably easier than what we did in Physics 1. Maybe they're exactly the same level of difficulty as what we did in Physics 1. So hopefully this is an easy section for you. And then also to the reminder, when you want to get the moment of inertia around a point O, use the parallel axis theorem to kind of convert the moment of inertia from the center of mass to point O. All right, so those are kind of the summary equations. So make sure you kind of have those in your mind as we proceed. All right, basic strategy, choose coordinates. Tangent normal is going to be the best coordinate choice. You want to have a good free body diagram for all the external forces and couples. You want to then calculate the moment of inertia, either about the center of mass or G, whatever's appropriate. And then you want to write down the three equations. So you have F equals ma for x and y, or in this case, tangent and normal. And then you're going to have the moment equation. So that's 3. And you just solve it. The other little twist, which you might remember from Physics 1, is that when you have things which roll or rotate or without slipping, then you can correlate various linear quantities with angular quantities. And so that's sort of a problem-solving skill. You have to just probably solve a few problems to kind of remember how all that works. And so that rolls without slipping condition helps you. Okay. So the first example I did was a rod that just falls straight down, and it was pretty simple. It's really just like a Physics 1 question. All right, and there you go. And then we also solved in the video. I solved. Oh, sorry. Here's their solution. It matches mine. So watch the video and you can see that. Here's another example where you have a board or beam which is it's balanced. It's in equilibrium. There's a pinned point or a pivot point here, and then at some point the rope snaps. And so what the problem wants you to figure out is what is the acceleration in that very first moment. And you can assume it starts from rest, and you just kind of work through the details of that. So I think so I chose in both of these problems, really I made I summed the moments about the pinned point, and so I'd use parallel axis theorem to get the moment of inertia, and then once I found the angular acceleration, I could work backwards and figure out what the what reaction forces were generated at the pin. So that's kind of the logic or the flow of how the problems went. Are there questions on that for anybody who watched the video? Were there things that were not clear? No questions. All right. Well, in that case, let's go to our, oh, there's my solution, sorry. Okay, let's go to our concept quiz. We have a rigid bar of length L, and it's released from rest in the horizontal position up at theta equals 0. And I want to know when the magnitude of its angular acceleration is maximized. At what angle? Does it happen at 0, 90, 180, or D, 0 and 180? Thank you, bud.
It's clean.
It is.
Fresh.
I know, it's pretty neat. Put it back in your room though, because carrying it around is a good way to lose it. All right. So when is the moment, or sorry, when is the angular moment? When is the angular acceleration maximized? At what angle?
I'd say 0 and 180.
So let's raise our hand here. So how many people, raise your hand if you think it is at 0? What about 90? What about 180? Oh wait, who said, were you guys raising your hand for 90? Okay, and what about 0 and 180? All right, so it's a bit of a mix, but I think D has the most votes. Oh, excuse me. And D is the correct answer. So the angle is measured from the top. So when the lever's all the way at the top, think about it here. You have gravity is going to create a torque. It's going to go down. And the same would be true if I were to rotate it the other side. But if it was vertical, well, the force of gravity is in line with the moment arm, and so there's no torque produced by the force of gravity. And so the angular acceleration here would be 0 when it's just vertical. So at 90 degrees, there's no moment. And it's maximized, the magnitude of it is maximized at 0 and 180. There are questions about that? All right. And it says in the above problem, when the angle is 90, the horizontal component of the reaction at pin O is, so the horizontal force generated up here at the pin, is it A, 0, B, mg, C, m, L over 2 omega squared, or D, none of the above? So the horizontal component, raise your hand if you think it's A. Okay. What about B? Raise your hand if you think the answer is B. What about C?
What about D?
What about D? None of the above. All right, didn't quite get everybody there. How many? Okay, that's all right. So the answer is 0, right? The horizontal component of the reaction. Well, we've said that when the angle is 90 degrees, there's going to be the force of gravity straight down, and we know there's no acceleration from side to side, and so then there can't be any force generated at the pin. What would option C refer to? What would option C refer to?
Is that the centripetal force?
It is well, yeah. So it's a centripetal term. So is that going to be a tangent or a normal component?
Normal.
Normal. And a normal component of what point on the rod?
Center point.
Yeah, the center of mass. Right. So remember, the force of gravity and all that will be constant. It acts as if it's at the center of the object, and then this is mass times acceleration for the central point.
Sean, so I guess a question I have real quick about like the first question here. So when it's at 90, would like the center of gravity acceleration be the greatest though? Because if it's like whipping around there, if it starts from the top and then
Shane, you're talking about velocity.
oh, so the velocity there would be the maximum though at 90.
There
Okay,
you go. Yep.
I think that's what I was getting a little confused on there.
So it starts from rest, goes faster, and then slows down. But that means so the velocity is minimized at the top, maximized at the bottom, but the rate of change of velocity is the other way.
Okay.
Yep. All right. So we're gonna have two group problems today. They're both kind of easy, I think. I gotta find it here. All right. So, all right, I'm gonna put it here. We will. There you go. So, all right. So I enabled private chats. Only say good things about me. Here's the problem, and then you guys can chat with your partners. I don't think the group thing worked very well. It's just too hard for me to kind of get around to every group. Here's a scenario. You have some sort of like a springboard, kind of like a gymnast springboard. All right, and you have a 4 kilogram slender rod initially supported horizontally by a spring at A and B. So it's just sitting there, everything nice and balanced. And then at an instant, 100 Newton force is applied right in the middle. And they want you to determine the angular acceleration at that moment, like at the instant where the force is applied. All right, so take a second, and I want you to chat with the person who normally would sit at your table, and figure out. Oh, and so find the angular acceleration and the acceleration of the rod's center of mass. And so those are the two things I want you to do. So take a second, let's say 3-4 minutes, talk through with the person you would normally sit with, and you can use the private chat option there, to come up with a plan for solving for alpha and the acceleration of the center of mass. Okay, so for some group that came up with a plan. Can you kind of describe what your plan was?
Well, the first thing that I'm doing in this is wait a second. Sorry about that. My brother was just had music on, but yeah. So
right.
yeah, nah. So the first thing that I was thinking of doing was, I know you can do a lot of things, but what I like to kind of do is I like to start off with a moment equation. So I do the moment about point A, so then I can find the frictional force, because you know that the 100 newtons going down, and you know the mg at the center of gravity, and then you don't know that frictional force is going to be pushed up. So that's kind of how I went about it.
Wait, what frictional force are you seeing?
Or not frictional force, I mean spring force, my bad.
Oh, okay. Yeah.
I
So
did
you're
that
talking
to
about
find the
before
spring
you,
force.
you're saying before you load it with the 100 newtons? Or what are you talking
I
about?
actually did. So at the moment the 100 newtons being applied, I summed the moments about point A to find the spring force.
Okay.
I don't know if that's like a good first step, but I did that just because I knew that we were going to need it eventually.
So you sum that moment, and you
About
set it
point
equal
A.
to what?
Some of the moments about point A is going to equal the moment of inertia about point A times alpha.
Okay. So now you have two unknowns, though. You have the spring force and you have alpha.
Oh, okay, yeah, my bad. I guess that might not be the best way.
Well, it will work, but you just have to plan it through. So you got two unknowns. So you're going to need another equation. What other equation could you get? Well,
So I got one of my questions on these type of problems is, so how would you know, because I know some of the problems the normal is zero. How do you know when the normal force is zero, or the normal force?
I would assume that the normal force isn't zero. It produces no torque. That's the thing that's there. If you see a contact, you probably should assume there's something going on there, unless you know it's like just about ready to tip or something. So maybe I'll describe how I did it.
Tell him to
And
share
then-
a screen.
So the way I did it was I said, okay, before the 100 Newton force is added, it's in equilibrium, right? So if that's the case, before you add the 100 Newton force, the weight of the rod down must be equal to the upward forces from the spring and the normal force. Furthermore, because it's a symmetric problem, I know, and nothing's moving, anything like that, no rotation, then I know that the spring force has to be exactly equal to the normal force, and each of them is half of the weight. So I basically said, before you add the 100 newtons, it's all in equilibrium, and the spring carries half the weight. Okay, and then, so then I knew the spring force. And then I said, okay, the normal force plus the spring force will add up to 0 in that instant. And that will be true because even after you add the 100 Newton force, because the only way for the spring force to change is if it compresses. And we're still in that first moment before it's compressed. So therefore, I actually just said the entire moment about point A comes from only the extra 100 Newton force. Because the others zeroed out, because without the 100 Newton force, they were in equilibrium. So that's how I thought about it. Did anyone else think of it a different way? No? Okay. So, all right, let's take another couple minutes. Oh, excuse me. And try to work through the algebra. And let's see what numbers you guys get.
So since it's the moment right when the 100 Newton force is placed, you can just ignore the spring force you said? At just that instant.
At that instant, yeah, because
Okay.
in order for the spring force to be anything other than its initial value, the spring would have to compress.
Okay.
But if we're just in that one instant, then it's okay. Yeah, that's how I did it. We'll look at how they did. The book did it also, and I think they did it slightly differently. The results the same, but
I don't know. It just doesn't make sense to me how anything before the 100 Newton force is added comes into play, because as soon as you add that force, the spring's force is going to change, isn't it? Isn't the spring going to compress as soon as you add that force? So what is it before?
well, okay. You remember from physics 1, there's always some time for it to happen. So as you apply the force, then the spring would want to kind of sag down. But in that first instant, before it has a time to move at all, the spring force can't change, because Hooke's law says the spring force is minus k times the compression. So if you don't give enough time to compress, the spring force can't change.
Okay.
And that's okay, because what's going to happen then is that extra 100 Newton force is going to create an imbalance, and it will accelerate. But it has generated an acceleration, but it has not generated a velocity yet.
So the key is that it's right the second after you add it is what we're looking for.
What'd you say?
I said the key is that we're looking for it right the second after we
Yes.
add the force.
Yeah. If you do anything other than that, they have to tell you all sorts of numbers about like the size of the spring and how much it's been compressed and the angle. It gets really complicated.
Okay.
Yeah. Is there anybody who's stuck? We can do a private chat. I can help you. Just raise your hand if you're stuck. Okay. Okay, we'll go 2 more minutes here. Is there anyone who's done? If you're done, raise your hand just so I kind of know. All right. Okay. so weird waiting. I'm the only one in the room just staring at the screen. All right. Raise your hand if you're ready for me to kind of start working through it, I guess. Or if you're sorry, let's do it the other way. If you need just a few more minutes, just how about you raise your hands, give you a chance to finish it on your own if you can. So raise your hand if you're almost there. One. Okay, I'll wait. Okay, so I'll wait just a second. Okay. I'll go ahead and switch over the whiteboard. Space. Okay, so I'll go ahead and start working through this one. We have the following kind of picture. We have a pinned beam. We have a spring. It's supposed to be horizontal there. We are told a spring constant. Is a spring constant relevant in this? Did anyone use the spring constant? I don't think so. I suspect they pulled this from in the book, maybe a larger problem where you had two parts, maybe before it started to move and then after it started to move. So they give us the spring constant. We don't need it. So don't worry about that. We know the mass is 4 kilograms. And we know the total length is 3 meters. And we're told that the force is applied right in the middle. Okay. So I'm going to solve it the way I described, and we'll look at how they solved it to give you a different, I don't know, line of attack. So we want, whoa, can't spell. We want alpha and the acceleration of the center of mass. And okay, so to do that, let's kind of work out how things are before. So the truth of it is, I don't actually need to know what the spring force is. I can work it out without that. But since it's not too hard to get, I'm going to say that at the start, the normal force from the point A equals the force of the spring, which has to equal mg over 2. So that the spring and the pin each support half of the weight, because the problem's nice and symmetric. If it wasn't symmetric, you'd have to work a little harder to figure this out. You have to sum Newton's laws and whatever, but you'd get there eventually. So these are numbers that we have. We could type them in if we want. Now, my logic was this. We haven't let this thing move at all, so the spring force can't change. And so that means that if I sum the moment about A, so when you apply the 100 Newton force, the normal force at A could change immediately. But if I sum the moment about that point, the normal force won't matter. Okay, so there's that. So after,
Sean, you said, how do you get to mg over 2 again? Sorry, I was.
well, Mohammed, the normal force and the spring are on the two ends.
Mm-hmm.
So they're symmetrically applied to the board.
So you just divide them by 2.
Yeah, they're just half the weight. Yep. So after the 100 Newton force is applied, I would draw a free body diagram where I would sum the moments about point A. So you would have some sort of a normal force. You would have a downward 100 Newton force. You would have an upward force of the spring.
So do you ignore the weight when you add the 100 newtons?
Do I ignore the weight? No. You have to add the
Okay.
weight as well. Thank you. Yeah, so that has to be in there. So at the beginning, before you add the 100 Newton force, was it rotating about point A? No. So that means that the torque generated by the weight plus the torque generated by the spring must add up to 0. So I'd say the torque from the weight plus the torque from the spring add up to 0. Which means for the purposes of finding the net torque after you add the load, well, you only have to focus on the 100 Newton force. So I can immediately say that the net moment about point A is simply going to be the 100 Newton force times the distance, L over 2, which would be 1.5 meters. And I would look at that and say that's going to be a negative moment because it makes it want to rotate clockwise. And that has to equal I about A times alpha. The moment of inertia, so the pivot point is here. What's the moment of inertia we should use? Does anyone remember off the top of their head? It's a rod rotating about the end of it.
Wait, this is the 1/3.
Yes, it is.
1/3.
So I know the
Mars.
moment of inertia is 1/3 the mass, which was 4 kilograms, times the length squared. So that would be 3. Whoa, sorry, squared. So that's going to be 12 kilogram meter squared. All right. So now I just solve it. So I'm going to get 150 divided by 12. Didn't screw that up. Oh, wait, did I forget to multiply by? Yeah, that's right. Yep, works out. So I get, times alpha. Oh, sorry, that was okay. I need to plug that in, and I get minus 150 Newton meters equals I, which is 12 kilogram meters squared times alpha. So we get alpha equals negative 12 radians per second squared. 12.5, sorry. Negative 12.5 radians per second squared. Okay. Raise your hand if you got the same answer for alpha.
What I did is I tried summing the forces in the tangential direction.
Okay.
Why did I get something different? Because I just said that the sum of the forces was just the 100 newtons, and then I divided it by the, what would the R be in that situation? Because that'd be mr alpha.
Were you using a force equation or a torque equation?
I was just using the sum of the forces in the tangential direction.
So you would want it. What are the forces in tangent would be kind of in the direction of the center mass is moving. So that's,
That would just be straight down then, right? So then it would just be
yeah,
100 Newton force.
100 Newton force. You also have a normal force from the pin. You also have the weight.
Those add up to E0, don't they? Because it was in equilibrium right before, so it would just be 100 force.
The torques. All right, yeah. So let's think about that. All right, good. So when you add that 100 Newton force,
Mhm.
The spring doesn't adjust. It doesn't have time to adjust.
Mhm.
But the pin, it's a rigid thing, so that can adjust immediately. So so when you add the 100 Newton force, the force at the pivot point will change, but that doesn't give you a torque. So you can only ignore the other forces in the torque equation, not in Newton's second law equation. I should have made that more clear. Nick, so think about if you I don't know, it would take, have your pencil like on a desk, right? And your hand could be like the spring holding it off the edge. So I'm kind of like holding it like this. When you push your finger on it immediately, there's some give in your hand, but at the point where it touches the table or the desk, that's immediately changed. Okay, so if you want to use force laws, you're going to have to know the normal force coming from the pin in the context of the 100 Newton force, but the only way to get that is to go to the torque equation. So you have to go to the torque equation. Okay. Is that all right, Nick? I think maybe I didn't explain that very well.
Sorta.
Okay.
I just don't see how, if that's the case where it's changing the pin right away, I don't see how then we could apply the moment. I don't see the.
Oh, because if you sum the moments about the pin, how much moment does that normal force give you?
None.
Regardless of how big it is.
Oh, okay. So if we didn't sum the moments about A, if we tried to sum it about the.
Why would you choose a kick in the head?
Okay,
Yeah.
that makes more sense now.
If you do another point, what you have to do is you would have to use both the torque and the force equation, and it'd be two equations, two unknowns. You'd have to solve them simultaneously. You couldn't just look at one and get the answer. Yep.
Okay, that makes more sense.
Yeah, don't avoid the torque equation though. Usually that allows you to proceed even when you don't have the full information. Okay, so that's alpha. And then they also wanted us to find the center of mass acceleration. So for that, so here's draw my picture again. All right, I know alpha is negative 12.5 radians per second squared, and the center of mass just follows a circular arc. So I know that the A normal should be the radius, which would be L over 2 times omega squared. But in that first instant, before it starts to move, omega is 0. And then A tangent is simply going to be the radius times alpha. So it's going to be L over 2 times alpha. Oh, and there's a funny thing. You guys are probably, when you guys are doing curvilinear things, when you want to talk about the tangent direction, you define the forward direction as positive, which actually has an extra minus sign. So we really want to look at the magnitude of alpha to get the numbers to match up.
So, Sean, why did you say that the normal acceleration was 0? Is that just because it's starting from rest at omega? Okay.
Yep. That's right. That's exactly right. So, good. So then I just multiply these things out. Just multiply 1.5 times that, and I get the tangent acceleration to be, just copying from my notes here, 18.75.
Now that we do know what the alpha is, could we apply the sum of the forces of the tangential to figure out how much of that pin changed?
You bet. Why don't we do that? Oh, come on. I'm choosing the wrong tool. I keep trying to write with the eraser. 18.75 meters per second squared. Let's try that. That wasn't what they asked with.
You forgot a negative sign, Sean.
Well,
we-
no, I put the absolute
What?
value in there.
Oh, that doesn't count though.
I put it in there.
Oh
right.
my.
I tell you what, Nick, we have to do another example. Running out of time, so I'll have to just leave it there. Yeah, you're right. You could work backwards and find the force at the pin now. All right, let's go. We're going to do another one. This one I won't have as much time to give you, so I'll have to kind of work through this. So here's how they did it, incidentally. The same Freebody diagram. They summed the moments about A, and you'll notice they kept all the forces around. They didn't just ignore the weight or other things, but they didn't even highlight it, but several of these things just happened to cancel. So, and they get the same answers. So even though, so they didn't really notice that the things canceled. I think they just typed it all in the calculator once and got their answer. Okay. Let's do this problem. All right, now I'm going to just do it because we're about out of time. It's kind of similar problem, really. The main difference is that now we have a rope. So imagine it's in equilibrium, so it's going to start from rest, like before. When this rope snaps, the main difference is now we have a complicated shape. So what we need to do is, what I would do is first find the center of mass for the total shape and find the moment of inertia for the total shape. And then after you do that, it's pretty easy because the only force that generates a moment about 0.0 is the weight of the total shape. And remember, the weight is always applied as if it's just concentrated at the center of mass. Okay, so are there any questions before I dive into this? We don't have that much time. So I'm going to find the center of mass for this whole shape, find the moment of inertia for this whole shape about 0.0, and then I'm going to sum the moments about 0.0, and the only moment we get is coming from the weight. All right, so I'm going to dive in and do that. I will go to the whiteboard. Oh, I'll give you the numbers as I write it all down. All right, so the picture we have this ball kind of hanging. We have a rod, a hinge, and then this has a length of 2 feet, and my ball is not to scale. The radius of the ball is supposed to be 1 foot. Sorry. So the ball is supposed to be, well, all right, sorry, bad artwork. So it's 1 foot. I'll write that over here. And I'm told that the mass of the rod is 10 pounds, which pounds of mass, which means if I convert it to slugs is 0.311 slugs. And the mass of the ball is 30 pounds, which I convert to 0.93, should be 33 slugs. Okay. And we're going to cut this, and it's going to swing down. So we want to solve for, well, we want both. So we want, in this problem, we want alpha, and we want the reaction force generated at 0.0. Okay. In that first instant when you cut the rope. So first thing I'm going to do is find the center of mass position. So let's do that. The center of mass position is going to be, well, because it's the numbers are nicer, I'll use the pounds rather than the slugs. I can write that as 10 times, so that's for the rod. Well, the center mass of the rod would be at 1 foot plus 30 times, and I would have 2 plus 1. So that would be 3 feet divided by the total mass of 40 pounds. And that's going to give me 2.5 feet. So the center of mass position relative to point O is at 2.5. So it's like the center of mass is actually kind of right about here for this whole combined shape. Right? That's going to be a number we need. Okay, so then let's see here. The next thing I'm going to need is to find the moment of inertia for the whole thing. So to do that, what I need to do is, well, let's think about that. I need to shift the sphere. I need to find the moment of inertia for the sphere centered on the red dot. So that means I have to shift it by 0.5 feet, 6 inches, and I have to shift the center of the rod by 1.5 feet. So I'll write that down here. So to use the parallel axis theorem, shift the sphere by half a foot and shift the rod by 1.5 feet. Are there questions on that point? That's kind of the, I don't know, maybe the trickiest thing. The rest of it's pretty easy.
There was a question on the homework that was like exactly like this, I think.
Oh, really? Okay.
Yeah, with the same like pendulum, except it was just hanging vertical.
It's a pretty typical configuration. So, all
I
right.
guess what I don't understand is why we're trying to bring it to the center of mass and not to the point O. Isn't O where we're rotating about? Because then the sum of about O could be the
Hold on.
alpha.
Nick, you are exactly right. I'm being an idiot. You're exactly right, Nick. I should go from the center of the object to O, because I want the moment of inertia about point O. You're right. I'm doing this wrong because I've started with finding moments of inertia, not by summing the torque equation. So I'm getting lost in it. All right, does everybody see where the mistake I made? I want to sum the moments about point O, so I need the radius not to the center of mass, but I need the radius, I need the distances to back to the O, because that's the point I want to set up Newton's laws around. So in that case, let's think about this. For the sphere, I have to move the sphere, not half, but I have to move the sphere, that would be 3 feet, because I have to take it all the way to O. And then I have to shift the rod not by 1.5, but by 1 foot.
Can we just use the 1/3 mr squared for the rod?
You could do that. Yep, that would work. Yep, that would work. All right. So for the sphere, so I for the sphere about point O is going to be I for the sphere about its center of mass plus mass of the sphere times 3 feet squared. And you're right, Thomas. We already know because it's a rod. We could say I for the rod is simply 1/3 the mass of the rod times the length of the rod squared, which would be 2 feet squared. Right? Does anyone remember the moment of inertia for a solid sphere?
Was it just mr squared?
I think
No,
it's 1/2
no.
mr squared.
That half is for a solid disk. Mr squared is for a ring or a point mass. For a sphere, it's 2/5. So I for the sphere will equal about point O will be 2/5 mass of the sphere times the radius of the sphere.
It's a nice 2 you got there, Sean.
Well, I'm doing this with my feet, so you should be really impressed that I could write this well with my feet. Times the mass of the sphere times 3 feet squared. When I plug in numbers, I think I have this all written down. No, I don't. Did I? No, I just did it all together. All right. So that's what I have. You need to use slugs, not pounds, mass. And then for I for the rod, about point O, that's going to be 1/3 mass times the length squared. Add them together, and the answer I get is 9.17 slug feet squared. All right, so that's the moment of inertia of the whole object in total. That's the whole thing. When you add them together, that's what you get. And now I draw my free body diagram. So I'd say, okay, there's there's point O. I have a rod and a shape, but the center of mass is out here at 2.5. Oh, change colors. Okay. And well, there's no other force acting on this. So there's just the weight. And so I can sum the moments, which is just the moment from the weight. The moment from the weight is just going to be the total mass times g. And if I look at it, this is going to make it have a positive rotation. So it'll be a positive moment. And that times 2.5 feet. That's the moment coming from the weight. And that's all you get. So that must equal so you sum the moments, that's got to be it's got to be I times alpha. So that's got to be I times alpha. And I know I, and I can type in the numbers here, and I solve for alpha, and I get alpha to be 10.9 radians per second squared. Okay. Are there questions for how I went about this? We're kind of at the end of our time here. So I summed the moments about point O, but the only moment I get is from the weight of the combined object. And I set that equal to the moment of inertia of the combined object times alpha, solve for alpha. And then if I want to solve for the normal force, kind of like what Nick was asking about for the last problem, I would add up the forces in the, there's no force in the y direction, but sorry, in the x direction, but I would get forces in the y direction. I have a weight down, I have a normal force going up, and well, that's it. I have a normal force and a weight. I know the weight, and that has to equal, when I add them up, it has to equal the mass times acceleration in the vertical direction. Well, that's just going to be r times alpha. So I just write all that down. So I get F net in the y direction is going to be minus mg plus the normal force coming from O, and then I get that has to equal minus r, which would be the radius to the center mass, times alpha, which is 10.9. So that's r alpha, oh, times the mass.
Hey, Sean, what was the reason for the minus sign there?
Oh, I'm in the y direction. So the weight is mg.
Oh, okay.
It's going to be down. The normal force will be up. And the acceleration of the center mass is going to be down. And then, so that's r times alpha, and I need a mass here. And so I want to use the mass, the total mass. You have to add that up. Trying to find where I wrote it down.
Total mass was 40.
Well, pounds, you got to divide by 3.32.2.
I think it was like 1.2, maybe.
Yeah, that sounds about right. So the mass will be like 1.2 slugs. Right. So, you know, this will just come out to be 40 pounds of force, the total weight. And this is the mass, is 1.2 slugs. You know everything, you solve for the normal force. And when you do that, you get 6.13 lbf is the normal force. Okay. Sorry, I'm running late. I'm just kind of over time here. But that's how it would proceed. And Nick, the last problem would have been exactly the same, like copy paste the method. You'd find alpha, back substitute into the force equation, and get whatever unknown force you want.
Yeah, that makes a lot more sense now.
Okay. All right. All right. There are questions about that. I know I'm kind of rushed here. Does it make sense? All right. Let's go back to the PowerPoint. And let's see how they proceeded. Some of the moments, yeah, they actually kept the objects pretty much separate the whole way. So they didn't combine it to find the total moment of inertia for the whole object. It looks like it's kind of, they must have done that. I must be misreading it. Anyway, yeah. You can watch the video and see how they do their algebra. It's a little different. In the end, we get the same answers. So it doesn't matter how you slice it, you always get the same place. Yeah, so when they were calculating the torques, the moments, they calculated the moment from each weight separately. And then, but when they found alpha, of course, you had to find the total moment of inertia. All right, here's a good one. Attention quiz. You have a thing that spins. You have two situations. One where you apply a 40 Newton force, and one where you hang a 40 Newton can off the edge. Rank the angular accelerations. Will the top one be, Finn, you have to be quiet here, bud. Will the top one be faster? Will the bottom one be faster? Will they tie, or none of the above? How many people think A, the top one will have a bigger angular acceleration? How many people think B, the bottom one will have a bigger angular acceleration. How many people think C, they will tie? How many people think D, none of the above? And how many people can't tell? That's fair enough because we're going pretty fast. Here's what I want you to think about. If this thing is accelerating around, then the mass will also be accelerating down. But if the mass is accelerating down, that means that the weight must be less than the tension force. Right? If this can is accelerating down, the weight of the can is less than the upward tension force, in which case the tension is less than 40 newtons, in which case angular acceleration B must be smaller than A. It's a little tricky. Okay, so the best answer is A. What happens is when it's accelerating, it's like the full weight is not communicated through the tension to the pulley. Only you get a reduced force. In case B, what is the tension on the cable? Well, all right, it's going to be less than 40. That's what I just said. All right. Sorry for going so fast here at the end. I'll post the next video, and it will cover both rotational and translational motions. And that'll be what we talk about next time. So make sure to read 17.4, 17.5. Stay up on the reading, and I'll see you guys then. Hey, Tim,
Yeah.
I wanted to ask you about.
You want to stop the recording there?
Yeah.
I'm raising